If you throw a bucket of tennis balls at a wall with two vertical slits, their behavior is easy to predict. The solid objects passing through the gaps land in two distinct clusters on the back wall. However, if you replace the solid balls with water ripples, the outcome changes. As a continuous wave hits the barrier, the two slits act as new sources, splitting the ripple into two separate arcs. These new waves overlap on the other side. Where two crusts meet, they reinforce each other to create a higher peak, but where a crust meets a trough, they cancel each other out. This geometric overlap creates a specific pattern of high intensity and complete stillness. In 1801, Thomas Young proved that visible light follows these exact rules. By shining sunlight through two narrow slits, he produced an unmistakable interference pattern of bright and dark bands on the screen behind them. By the 19th century, the physical world seemed to have a clear divide. Solid matter travels in straight, predictable lines, while light travels as continuous, overlapping waves. In 1905, Albert Einstein observed that light could knock electrons off a metal surface, a phenomenon known as the photoelectric effect. This interaction revealed that light actually arrives in solid, indivisible packets of energy called photons. Decades later, Louis de Broglie proposed the inverse, that solid matter, like a single electron, possesses its own physical wavelength. This discovery created a paradox. If light is made of localized particles, it shouldn't be able to fan out and interfere, and if an electron is a solid object, it shouldn't possess a wavelength. To investigate, physicists upgraded the double slit setup for the subatomic scale, firing individual particles one at a time to see what happens when they have no other particles to interact with. In this modern iteration, an electron or photon is fired with a long pause before the next one follows. This ensures that only one particle is in flight at any given moment. Initially, the particles strike the detector in a scattered, random arrangement of individual dots. But as thousands of these individual hits accumulate, they arrange themselves into a striped interference pattern. Even though the particles were fired alone, they collectively build a signature previously reserved for continuous waves. Richard Feynman explained that a single particle takes a sum over paths, simultaneously exploring all possible routes through both slits. In Feynman's framework, the wave is not a physical substance like water. It is an immaterial wave of mathematical probability. Each particle exists in a state of superposition, acting as a wave of possibilities until the moment it hits the screen and becomes a concrete, localized dot. Physicists then added a detector next to the slits to watch the particle and confirm which path it actually takes. The result was immediate. The moment the measurement occurred, the wave interference pattern vanished. The stripes on the screen collapsed into two plain stacks of hits, exactly like the tennis balls from the Cossical experiment. In the delayed choice quantum eraser variation, researchers found that even if the path information is measured after the particle passes the slits, the wave still collapses. This is the measurement problem. The universe refuses to act as a wave if path information exists, proving that the act of observation changes the physical result. Science has struggled to explain the mechanics of this wave collapse for over a century, leaving the community deeply divided. The Copenhagen interpretation, championed by Niels Bohr, posits that subatomic objects have no physical reality until a macroscopic measuring device forces them into a classical state. The many worlds interpretation avoids wave collapse entirely. It argues that the universe continuously splits into parallel realities to accommodate every possible outcome of a measurement. While some interpret this to mean a conscious mind affects reality, the observer effect is strictly a result of detectors exchanging physical information with the system. Physicists still debate the philosophical why behind the collapse, but the mathematical how is incredibly precise and consistent. This duality is the engineering foundation for the machines that define the modern world. Electron microscopes actively exploit the wave nature of electrons to image individual atoms at scales far beyond the reach of visible light. Without this understanding of quantum behavior, we wouldn't have lasers, fiber optics, transistors, or MRI scanners. Quantum computing represents the next step in this progression, holding data in the same wave-like superposition as the unmeasured electron. As Feynman noted, this single experiment contains the only mystery of the quantum world, a behavior that governs the basic mechanics of every atom in existence.